Hello friends, myself Rutu Patel, lecturer in chemistry from Parul Institute of Engineering and Technology Diploma Studies second shift, welcome you all to the active learning session on the chemistry. Today we will recollect the last information and go ahead in the atomic structure chapter number 1 with starting of the Aufbau Principle. That is, we have to recollect first. Your Aufbau Principle states that electron enters into lowest energy orbital first and then high energy orbitals are gradually filled. Means what? Your electron is going to first enter into 1s orbital. Once this 1s orbital is fully filled, it enters into 2s, then into 2p, then into 3s, then into 3p, then into 4s, then into 3d. This we have seen into the last session. Aufbau is a German word that deals with, that is actually having the meaning of the construction. Now you should be aware that your 1s orbital is having the lowest energy here. That means energy of the 1s orbital is less than 2s, less than 2p, less than 3s, and so on. The energy of the orbitals are defined by the Aufbau principle. Now we have also seen by how to write the configuration actually. That is, we have seen the intake of the different orbitals along with the Aufbau rule. That is, your s orbital can take 2 electrons, your p orbital can take 6 electrons, your d orbital can take 10 electrons, your f orbital can take 14 electrons to the maximum limit. Once we define the intake of the electron for different orbitals, after that we can recollect it by linking it with the Aufbau rule. See, for writing the configuration, your hydrogen having atomic number 1, so what we will do? We will take the 1s orbital first, then we will write your electron is 1, so we will write as 1s1. In the second, helium having the atomic number of the 2, we will write the configuration as 1s2 because the second electron is again going to enter into your s orbital because your s orbital is not fully filled. Coming to the lithium, with the case we have seen 1s2, now your s orbital was having capacity of 2 electrons and it is fully filled. So what is the next orbital that comes? That is your 2s orbital. So what we will do? Lithium is having your atomic number of the 3, so we will write the configuration as 1s2 2s1. That means your lithium configuration, again the third electron is basically going to enter into 2s1 orbital. Now the next one, that is your beryllium. Beryllium is having your atomic number of the 4. So what is the configuration? That is 1s2 2s2. It means now if you see carefully, the 2 electron capacity of the s orbital is now over. So we have to take now new orbital, that is your 2p orbital. So for boron we can write it down as 1s2 2s2 2p1. That is the configuration for the boron. For carbon, the configuration is 1s2 2s2 2p2. Similarly, we have discussed the case for the nitrogen also as 1s2 2s2 2p3. For oxygen, we have discussed the case of 1s2 2s2 2p4. For fluorine having the atomic number 9, we can see 1s2 2s2 2p5. Now this neon having the atomic number of 10, if we try to see here, it is having the fully filled stable configuration. It means your s orbitals are fully filled as well as your 2p orbital is fully filled. So this is acting as your inert gas because all the orbitals are fully filled, and that's why this element is included in the inert gas category. Now coming to the sodium, that is having atomic number of 11, we can write your 2p orbital is fully filled. So next orbital that is coming after 2p is basically 3s. So for sodium, the 11th electron is basically going to enter into your 3s1 orbital. Okay, that is the thing. Proceeding ahead with the next case, that is your magnesium having your atomic number as 12. So we will write as 1s2, 2s2, 2p6. Now recollect the Aufbau rule. What it was stating? You have Aufbau rule, 1s energy less than 2s, less than 2p, less than 3s, less than 3p, less than 4s, less than 3d. Now what is the next orbital that we are supposed to take? After 2p we are supposed to take 3s. So how many electrons will enter into 3s? That is your 2 electrons. Okay, this one has to remember for taking the case. Now if we try to proceed ahead, we will go to the aluminium, that is having atomic number of the 13. So what happens to this? This is having configuration. Look here, the 3s orbital is basically fully filled. So we will proceed to the 3p orbital now from 3s. So configuration will be 1s2, 2s2, 2p6, 3s2 and 3p1. This one has to remember. Now the electron is going to enter into 3p orbital, and you are aware that p orbital can take up maximum of 6 electrons. So we have to proceed according to that. Silicon is having the atomic number of the 14. So what we will write? It is having configuration of 1s2, 2s2, 2p6, 3s2, 3p2. Similarly, we can proceed ahead with the 15 number, that is your phosphorus. Phosphorus having atomic number of the 15, we can write here configuration as 1s2, 2s2, 2p6, 3s2, 3p3. Okay, then we will move ahead to the sulfur having atomic number of the 16. That is, you can write here 1s2, 2s2, 2p6, 3s2, 3p4. This is the sulfur having atomic number 16, and you can gradually, meantime, you can count also the electrons to verify that we are going right or wrong. You can see here 6 plus 4 is 10, 11, 12 and 12 plus 4 is 16. So the sulfur configuration is completed. Moving to the chlorine having atomic number of the 17. You can write here 1s2, 2s2, 2p6, 3s2, 3p5. Now your 18th atomic number having the 18 atomic number element is your argon. Argon configuration can be written like this: 1s2, 2s2, 2p6, 3s2, 3p6. Now if you look the case of the argon, then your all the s orbitals are completely filled as well as your p orbitals are fully filled. So again it is included into the inert gas category and having the stable configuration. So this argon is basically a inert gas. Now we can write it for the Similarly, potassium. So if we see the case, 3p orbital is now here fully filled because p orbital is having capacity up to 6 electrons. So we can now move to the next orbital, that is our 4s orbital. So what we can write here is 1s2, 2s2, 2p6, 3s2, 3p6, and the next electron will enter into your 4s orbital. So the configuration will come out to be 4s1. Or else we can write it like this, that it is argon 18 and 4s1. This can be written for the case of your potassium. Similarly, we can write it for the case of the calcium, that is 20th element. Calcium having atomic number of 20, you can write it down 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So you can remember here that calcium having atomic number of the 20 is having this much of the configuration. Now coming to the next topic, that is we can write the configuration in the numbers as well. So how to write it in the case of the numbers, that we can see, that is we will again start off with the first element, that was our hydrogen having atomic number as 1, so we will write it as a 1. Then helium having atomic number as a 2, we will write it as a 2. Then lithium having atomic number of the 3, we will write it as a 2, 1 configuration. Similarly, beryllium having atomic number 4, we can write it as 2, 2. Boron having atomic number as 5, we can write it as 2, 3. Carbon having configuration atomic number 6, we can write it as 2, 4. Nitrogen having atomic number as 7, we can write as 2, 5. Oxygen having atomic number as 8, we can write it as 2, 6. Fluorine having atomic number of 9, we can write it as 2, 7. Then your neon having atomic number of the 10, we can write it as 2, 8. Okay. Now sodium having atomic number of the 11, then we can write it as 2, 8, 1. Magnesium can be written as 2, 8, 2. Aluminium having atomic number 13 can be written as 2, 8, 3. Silicon having atomic number 14 can be written as 2, 8, 4. Phosphorus having atomic number 15 can be written as 2, 8, 5. Sulfur having atomic number 16 can be written as 2, 8, 6. Chlorine having atomic number 17 can be written as 2, 8, 7. Argon having atomic number 18 can be written as 2, 8, 8. Moving to the potassium, then 19 you can write here as 2, 8, 8, 1. Calcium having atomic number 20, you can write it as 2, 8, 8, 2. So it clearly specifies the electron into the outermost orbital, that is lithium having 1 electron in the outermost orbital, and so on for the beryllium, boron and different cases are there from this. Now we will move to the Pawleys principle, that is one of the important part. So we will write here, that is Pawleys rule. Now what does this rule states? It states that no two electrons in an atom can have all four sets of quantum number same. It means what? We have seen in the last lecture that there are basically four types of quantum number. The first was principal quantum number, the second was angular quantum number, third was magnetic quantum number, and fourth was spin quantum number. So what does this rule says? That electrons cannot have all the four quantum numbers to be same. If three quantum numbers are same, but there is a chance that the fourth quantum number, that is spin quantum number, is always going to be different. So we can write it here like this, that n equal to 1, n equal to 1, so L equal to 0, L equal to 0, so M equal to 0, M equal to 0, and your spin, if here it is plus half, then here it can be minus half. So this states that no two electrons can have all four set of quantum numbers same, and this is basically your Pawleys rule. So we have learned the three rules up till now, that is Aufbau Principle, Hund's rule and Pawleys rule, and the rules are different from each other, stating the position of the electron into orbital, as well as the different quantum numbers can be identified from these rules. Let us try to take the important concept of the ionization energy. Now what is this ionization energy? See, we can learn it like this, that ionization energy